So I will ask a lot of questions, but I prefer it to be like a conversation. So interrupt me if you like, or
right. Good.
So, well, the first thing, can you introduce yourself?
Yeah, I'm Juan Maldacena. I'm the Carl Feinberg Professor here at the Institute for Advanced Study.
And what exactly is your field of research?
My field of research is in trying to understand the fundamental laws of nature, trying to develop theories that connect space-time and quantum mechanics. And the main objective is to understand the beginning of the Big Bang.
Whoa, that's a big question.
Yeah.
But did you say the laws of nature?
Yeah. Yeah, so physics is about studying the laws of nature, so how nature works. Through the years, we've learned a lot about how nature works. And currently we have theories that are incredibly successful. One of the theories is the theory that describes gravity. So it was originally developed by Newton and then improved by Einstein. Einstein gave us the current equations that govern the behavior of space-time. We'll discuss perhaps a bit more what space-time is made of, or well, what the theory of Einstein tells us about space-time. So that's one very successful theory. It explained things like the expansion of the universe, the formation of black holes. It's phenomena that before the theory was introduced, where people even didn't think about them. And on the other hand, we have the whole set of theories that describe matter, the behavior of matter and the structure of matter. And these theories were the current version, well, especially the version that is quantum mechanical, started being developed in the beginning of the 20th century. And the quantum is very important for the description of matter. It's what keeps matter stable and prevents it from collapsing, prevents atoms from collapsing, and so on. And this theory was further developed through the 20th century, and it's now come to what we call the standard model of particle physics.
Okay.
It's,
particle physics.
Yeah, so it's basically the basic structures, basic constituents of matter. So matter is made out of little small particles that behave according to the laws of so-called quantum mechanics. What is remarkable is that this list of constituents is very small, so very small number of particles make up all the matter that we see.
Really?
Yeah.
So everything is built up from just a small number of
small
particles?
Yeah, of kinds of particles. So we have the particles that, the electron is one of them, and then we have the particles that make up the nuclei of the atom. Within the nuclei there are some particles called quarks, but they're small little particles. And for most of matter they are made out of just two kinds, so-called up and down quark. And then there are some particles that mediate the forces between them, the photon or the electromagnetic waves and so on. And then the weak force and the strong force. The strong force keeps the nucleus together. And with these particles and these forces, we can describe all of matter.
Do you know that, or you think so?
No, we know it experimentally, and the latest experiment was the experiment in the Large Hadron Collider, which discovered the so-called Higgs boson. That was one of the missing particles in the standard model, and so now we have a whole set of particles that describes everything. I briefly told you about the particles that make up most ordinary matter, but there are other unstable particles which are similar, but this structure gets replicated a few times. And so now we have a complete set of particles with a logically consistent theory that uses the structure of something called relativistic quantum mechanics. So relativistic quantum mechanics. So it's quantum mechanics plus the principle of special relativity. So we can discuss perhaps special relativity a little more.
Mm-hmm.
So let me discuss perhaps these theories a little more, and then we can go on into discussing perhaps the more current issues. First, we have these notions of space and time, right? So in principle, space and time seem totally disconnected from each other. So we have a very intuitive notion of space, while time looks a little more mysterious to us, and but certainly different from space. And so the first point I would like to explain is why physicists talk about space-time, why they put these two words together. Why don't they talk about space, temperature, space, I don't know, price of soy or whatever. So they talk about these two things because the way you perceive time depends on how you are moving through space. So if you have two observers who are moving relative to each other, the two observers perceive time differently. If you have a clock here, another clock that is moving, this second clock will appear to this observer as moving slower than this clock he has at rest. And the other observer will see the other clock also moving slower. And this can happen because space and time sort of get mixed by motion. This is the consequence of a principle, which is the principle that light, the speed of light is constant for these two observers. This is something that is not totally intuitive. So if you have one observer that is stationary, and you have a light beam that travels this way, and you have another observer that moves in this direction, naively, according to your intuition, you would expect that this observer should see the light moving slower, right?
Yes.
If instead of talking about the light beam, we were talking about the train, that would be the case, right? But it turns out that experimentally, the speed of light is constant, so it's the same for all observers.
Oh, really? So compared to the train?
Yeah. So if you had if instead of a train we had a beam of light, the two observers, one is stationary and the other is moving, both would see the light going at the same speed. So the light would be moving this way, and this happens because the rate of how time and space are perceived by the two observers is different. So the price you have to pay for this constancy of the speed of light is that time is now relative. So in the theory of special relativity, the speed of light is absolute, but time is relative. Time is relative to who's measuring it.
Well, I can try to understand what you're saying. So what I hear is that you say that the speed of light is constant.
Yeah.
So time is not constant.
Right. Time is relative. The flow of time depends on how you are moving through space-time. So it's similar to, let's say, space, right? So space. So if we are standing in space, there is some direction we call forward and some direction we call to our right, right? But if you have another person who's looking in a different direction, what's forward to him and what's to the right is different, right? So it's this exactly the same, but for moving observers. So you have two moving observers. What one calls time and space is different from what the other calls time and space.
Yeah.
So that's why it's more convenient to think about space-time as something that is both time and space, and that thing is the same for both. What one calls time and space is different, but space-time is the same, right? It's the universal structure on which particles move, right? The laws of physics have to have this symmetry of the constancy of speed of light, and the fact that the laws of physics should be independent of how you're moving. And when you combine quantum mechanics and this principle of special relativity, you get the modern theory of particle physics. You get the structure, which is called quantum field theory, and using special cases of this structure, putting in which particles you have and the interactions and so on, you get the models for particle physics. And they are incredibly successful, and they describe all the experiments that you can do.
So you raised, in the beginning you raised the big question.
Yeah. How
did the universe...
Right, so let me first say a few words about general relativity. according to our intuition, so space is sort of absolute. So and there is some pre-existing space where particles move and the objects move. That's probably the theory of Newton we learned in school, that planets move and so on. They are moving in some space that was pre-existing and is not affected at all by the motion of these planets. But in the theory of general relativity, what Einstein postulates is that space, or space and time, because they have to come together because of the principle of special relativity, they are actually a structure that is dynamical, so it can be bent by the presence of matter. And he further says that the force of gravity is due to this bending of space-time. So this is a new, very interesting conceptual idea.
Mm-hmm.
And again, it describes gravity as we see it, and it describes deviations from Newton's gravity. It describes new things that were not known at the time of Einstein, like the expansion of the universe, the formation of black holes in extreme circumstances. And, well, some of its predictions have now been confirmed, like the discovery of gravity waves very recently, just a week ago, that was announced.
Yeah, I saw that. Were you excited about it?
Yeah, that's pretty exciting and very interesting.
Did you know about that they were going to announce this?
Yeah, there were rumors that they were going to announce it. But yeah, of course, the experiment had been going for a couple of decades.
Yeah.
So
for a couple of billion years.
No, well, the gravity waves were going on for a long time, but the experiments trying to detect them also took a lot of effort.
Yeah.
And so that's also again a dramatic confirmation of both Einstein's theories, and moreover the existence of black holes. And this theory of special relativity, of general relativity, well, Einstein derived equations, but then there was a lot of research trying to understand the solutions of the equations, the physical interpretation of the solutions. For example, black holes were really only understood in the 60s, just even theoretically. And then understanding them better then led to understanding what things you should look for in the sky, and indeed some objects in the sky were recognized as probably candidates for black holes, and now we have this gravity wave detection, which appears to come from the collision of two black holes.
You think so? Or
Well, that's what the model to describe it. We've only seen they only announce one collision. Probably as they see more, it will become more and more convincing.
Yeah, because this is the first one, but it's a question of time that more of these.
You would hope, yeah. So that's all about Einstein's theory of relativity. So Einstein's theory of general relativity is a theory where space-time is dynamical. It's something that moves. It's not a static thing. It's an actor in physics somehow. It's not the stage on which physics happens, but it is the stage for all particle physics, for all the matter and so on. You have a space-time, and then matter moves in that space-time. But also space-time reacts to the presence of matter and moves itself. In cosmology, this expansion of the space-time is very important.
Mm-hmm.
For, space-time expands and it cools because of that expansion. So the expansion of space-time is very important for getting to the universe, what it is, and the structure of matter to what it is. This expansion is important for, cooling the universe, and then further, the force of gravity creates the structures that we have in the universe, such as galaxies and planets and so on. And so it's important for explaining nature as we see it. But Einstein's theory of relativity is in some sense incomplete, because it...
Incomplete?
Incomplete, in the sense that... incomplete in the sense that you can, if you start out with some initial conditions which are reasonable, the system evolves and creates so-called singularities. So you can solve the equations, and you find situations where the curvature of space-time becomes infinite. So this happens, for example, when a black hole collapses. In the interior of the black hole, there is a region with infinite space-time curvature. So if space-time becomes so curved and so the force of gravity somehow becomes infinite there. If you were to fall in there, you would be ripped apart. And we don't have a theory that, well, the current theories like general relativity and particle physics do not explain what happens in that situation. And so.
And are you looking for the explanation?
Yeah, so those are the theories we have. I think maybe we can make a small, because my family is coming in,
yes.
and maybe I want to tell them to be quiet.
We were at the point that you were trying to connect
Yeah.
the theories.
Yeah, so the Einstein theory works very well for many things we observe, but the equations themselves fail in certain situations. So one situation is when matter collapses in a black hole. So in the interior of the black hole, we get a region with very high curvature, and if you were to fall in there, you would be ripped apart. And the equations don't allow us to derive what happens to matter when that happens. And another interesting situation is if you evolve the equations backwards and you try to find out what happened in the very beginning of the Big Bang, also the current theories cannot explain what happens. So there, again, the expansion would be so rapid that space expanding so rapidly that you cannot derive what happens. The equations themselves, the curvature becomes infinite, and the equations fail. The reason, yeah.
No, if I try to imagine, of course, what's happening inside your head, trying to connect these theories, what happened?
Well, the main reason for this inconsistency is the fact that the Einstein's theory is a so-called classical theory, which is a good theory when things are very big, but when basically you are at very short distances, you have to take into account the quantum. In the same way that matter at long distances can be described also classically, but when you go to short distances, you have to describe it using the quantum mechanical description. Space-time is similar. When you go to very short distance in space-time, you also would need quantum mechanical description. So for matter, when we go to short distances, we go to the atoms, the elementary particles, and so on. For space-time, we should go again to something which would be like the atoms of space-time. And
what is that?
We think that if we went to such a theory, we could do this. We could perhaps understand the Big Bang or these situations which we cannot understand today.
If you find the atoms of space-time.
I can't define the atoms of space-time. We're trying to find what they are. And one idea that is wrong is the idea that there would be atoms at each different location in space and so on. So space-time is not like continuum matter, because one important property that was understood theoretically is that when you have the number of configurations in a region of space-time, that number of configurations does not grow like the volume as it would with ordinary matter. So the number of atoms, somehow, whatever they are, of space-time, we know that their number grows like the area of the surface rather than the volume. And so that's an interesting property of these so-called atoms of space-time. So by atoms of space-time, I mean, well, basically a vague idea, but I tried to motivate it in this way, the search for a theory that describes space-time at the quantum mechanical level, so using the laws of quantum mechanics. The laws of quantum mechanics are laws which are intrinsically probabilistic, so that's the main difference from the laws of classical physics. In classical physics, if you know the initial conditions, you can then calculate what will happen in the future.
Because you cannot do an experiment, you mean? You cannot.
No, in quantum mechanics you can do experiments, but the result, you can prepare the initial conditions always in the same way, but the results of the experiments will be different. Each time you do the experiment, you get a different answer. And all you can predict according to quantum mechanics is not the precise answer of the experiment, but the probability distribution for the different answers. So you doing an experiment is like flipping a coin, and you can calculate and you can say, well, maybe I'll get 50% one result, 50% of the time one result and 50% the other, or maybe it's 30, 70 and so on. And quantum mechanics allows you to calculate those percentages, but quantum mechanics doesn't allow you to give definite answers to some questions. And it is intrinsically this way.
But that's a rather big question you ask yourself. And besides the part that you are this scientist trying to research this, I'm also interested why is it you asking this question? So what's your why do you ask this question? Why do you do this?
Well, I certainly I'm not the first to ask this question. So this question was asked many years ago. Probably Planck was the first to realize that there was a connection between the quantum and gravity, and at some point gravity would fail, and calculated what distance scale it would fail. So that was maybe a century ago. And since then, people have had various ideas. We're thinking about this problem, and it's a problem that is hard to access experimentally directly, because this distance at which the quantum is important is super tiny. So it's much smaller than the smallest distances we can see today with accelerators. So I'm part of a group of people who are trying to investigate this from the theoretical point of view, trying to find a structure, a mathematical theory that would put these two things together. And we are trying to do something similar to what Einstein did when he joined special relativity with Newtonian gravity. So he realized that the gravity theory of Newton was not consistent with this idea that the speed of light is the maximum speed of propagation of signals, and that it should be the same for all observers. And putting those two things together, he managed to create a structure, the structure of general relativity. So here we are trying to replicate that, and from theoretical points of view, try to find the connections between the quantum and space-time.
And are you sure you are going to find the answers, or are you
no,
sure you're on the right track?
We're not 100% sure, but we are confident that we have a high probability. And the question is so interesting that we should try to investigate it.
But you know you're on the right path.
Yeah. So what gives us some confidence that we are in the right path is that we're not investigating this in the vacuum or without. We now have some very concrete theories. The nicest one is the theory of string theory. That is a theory basically under construction, but that works very nicely in some situations, and that manages to join the quantum with space-time. And it's a theory under construction and a theory which is continued to be developed, and we're trying to understand it. Yeah, string theory, yeah. So it seems to capture, at least it seems to connect the quantum with space-time in a very interesting way. And by investigating string theory, people have found very interesting mathematical relations that are true in mathematics. They found the connections between different physical theories. For example, between the theory of strong interactions and some theories of space-time. And the fact that these connections were found gives us some confidence that at least the structure that we're investigating is interesting and rich, and it could be the answer to this question of quantum gravity, which is really the main question we're trying to answer.
And you are in a group of people who are on the same level, theoretically.
Yeah.
So, but how is it for you to? Now you have to explain it to me, and I don't understand. So you have to transfer your thoughts or your ideas to people who don't understand, because it's so difficult. Even for you, for yourself, it's difficult. How is that?
Well, for us, it's difficult to find the equations but I think what I'm trying to convey is the problem we are trying to understand, and I think the problem is understandable. It's I mean, it's just joining two theories of physics that are out there and putting them together. So they are not completely compatible with each other. And in the history of physics, when there were two kinds of theories that were not quite compatible, and you find the structure that puts them together, it might be the right structure.
And this theory might be the string theory.
Yeah, so string theory is the main tool and the main thing that we are investigating. And we think that it is, if it's not the right structure, it's probably close to the right structure. It could be a stepping stone to the right structure.
For a lot of people, the string theory is ununderstandable. So, but you all have to understand the string theory just to use it as a possible.
Yeah. So string theory might sound complicated, but I mean it's something that someone who's doing his PhD in physics can learn in a year, a couple of years. So they can.
A couple of years, and then you know the string theory.
Yeah, that's right.
so maybe I can learn it in 1 minute. Can you explain to me what
you know, there is, it's like playing the piano, right? You're not going to be able to play the piano in 5 minutes. So, I mean, someone can tell you, oh yeah, you have to press keys and so on, but you won't be able to play the piano or to produce nice music.
And it sounds awful.
And so here also it takes a while to get to familiarize yourself with the ideas. And one reason it's hard is because you really have to learn a lot of the physics that precedes it. You have to learn well general relativity. You have to learn well the theory of interacting particles, and well, you have to do this. So
isn't it a fact that if different people from different backgrounds come together and discuss this string theory, that in the event that they all know what you are talking about, or understand the string theory, doesn't make it then true?
No, I mean, what makes a physical theory true as a theory of physics is comparison with experiment, right?
But if you all understand string theory and you think it's true, you understand what it means. Took some years, but the different other people also took some years and they understand string theory.
Well, string theory today is a mathematical structure, so it's a mathematical structure which has some physical interpretation, but we don't yet know whether it's the right theory of physics. We think it's in the right track, and we are motivated enough to continue studying it. But you know, that doesn't make it true. That just makes it a very interesting mathematical theory.
And can you explain to me what is meant by the string theory?
Well, mainly string theory is a theory with some laws and so on that can describe space-time at the quantum mechanical level, so using the laws of quantum mechanics, and that it reduces to Einstein's theory for big distances. That's its main advantage. Now, maybe you are asking why is it called strings? Well, this comes from the fact in one of the old versions. Well, this comes from the fact that in one formulation of the theory, you have little tiny vibrating loops of string. So instead of having particles which are point-like, as we have in theory of particles, ordinary particles, the elementary objects are little strings, one-dimensional objects, and that's and using those, you can describe ripples of space-time interacting, or those gravity waves that we discussed before in the experiment, when they interact in a quantum mechanical way. They can do so in a way that does not generate any inconsistency. So,
is there a theory of your own which you are investigating or researching?
Well, I've been researching a certain relationship between string theory and particle physics. So it's a relationship which is part of these connections that I was describing before that string theory led to. And so this is a connection between theories of gravity in the interior of a space-time and a theory of particles on the boundary of the space-time. So in this relationship, the idea is that the so-called atoms of space-time of the interior are like particles on the boundary. That's roughly one way to say it. another analogy people make sometimes is the idea of a hologram. A hologram is a two-dimensional photographic plate that when you illuminate it with light, you see a three-dimensional picture. So the idea is that you can have the dynamics of these particles on the boundary of space-time, so far away, can have an alternative description as objects moving in the interior, subject to the force of gravity.
So the atoms of space-time are reflected or projected?
Yeah, so the real atoms would be on the boundary, the real elementary particles, let's say, and then we get some effective description, approximate description in terms of a space-time in the interior. So in this picture, space-time emerges as an approximation, approximation due to the dynamics of lots of particles, in the same way that properties of macroscopic objects come from similar approximations, like the viscosity of water, or just the behavior of water waves and so on, comes from the collective motion of many of the constituent molecules, right?
So, but can you explain to me how it works, this hologram again? Mm-hmm. Maybe as simple as possible.
Yeah. So this idea is the idea that you can describe gravitational physics or dynamics of space-time at the quantum level, which is something we don't understand too well how to do it, in terms of a theory of particles that lives on the boundary of that space-time. The theory of particles is very similar to the theory of particles we use for particle physics, or some similar to the theories we use even in ordinary quantum mechanics. So that's this connection, and it connects, for example, black holes to thermal systems of particles at finite temperature, and if you assume, so it's a conjecture that these two things are related, and it's a conjecture that people have worked a lot on, and they found lots of evidence that it is correct, at least in very specific cases. So it's a conjecture that leads to it's a conjecture between two, let's say, mathematical theories. One is the mathematics of string theory in these spacetimes, or quantum mechanical dynamical spacetimes, as described through string theory, and ordinary theories of particle physics. And so in many cases we can approximately describe each of the two sides and then check mathematically that they are correct. But the idea is to understand this further, to understand better what this implies for space-time and how to build better theories of space-time. In particular, how to solve some of the problems we have with black holes. So black holes are understood reasonably well with the theory of with Einstein's theory of relativity, but black holes have also give rise to some quantum mechanical effects. Well, more precisely, once you take into account quantum mechanics, black holes can start to emit a kind of radiation that Hawking discovered, and he discovered this theoretically, and it's called Hawking radiation. And so this implies that black holes, they form, and then they start emitting this radiation, so they emit a kind of soft glow. And just to highlight how surprising this radiation is, so black holes were called black because they don't emit any light. I mean, everything that goes in has to fall in, and nothing can be emitted.
Can get out.
Cannot get out. But this radiation is something that is somehow getting out. And so you can even have the paradoxical situation of having a white black hole. So if you had a black hole which is tiny, very tiny, the size of the wavelength of light, or the size of a bacterium, roughly speaking, that black hole will look white to our eyes. Now, these black holes don't form naturally in nature. So the black holes that form naturally in nature are very big and have a very low temperature. But if you could form such a tiny black hole, theories predict that it should look white. So here you see that a little bit of a conflict between Einstein's theory of relativity. The beginning of a conflict, you see that. One says that it should be black, and the other one says it should be white, right?
White hole.
Yeah, this is different.
This
is different from what people call a white hole, but this is a white black hole.
Yeah.
And And here you see the beginning of some slight conflict between the two. And if you go a bit deeper in, there are some laws of, let's say, thermodynamics that should apply to black holes, to any object that emits thermal radiation. This radiation is thermal, so it gets emitted at a certain temperature. And that's why you needed to make it very small to make it look white, because the temperature becomes higher the smaller the black hole is. So small black hole is hotter than a bigger black hole. And so as you make the black hole smaller, it gets hotter, right? And if you apply to it the laws of thermodynamics as we usually understand them, they seem to hold for such black holes. But they seem to be in some conflict with another fact we know from general relativity, which is that if you solve the Einstein's equations in a black hole, there is a surface that we call the horizon, which is a surface basically dividing the outside and the inside. It's an imaginary surface. It's not a real surface. It's kind of point of no return. So if you cross the horizon in the interior, you cannot send any signal to the outside. So you cannot even escape. You will be doomed to fall into the singularity. But you don't feel anything when you cross the horizon. So it's a perfectly reasonable surface. And so that's what Einstein's theory predict. And this fact seems to somehow be in some conflict with these thermal properties of black holes. And how to fully resolve this conflict is one of the things I and some other people are working on.
And is there something that you can call your life work? Can you? Well,
I would say that it's been mostly investigating this relationship between the interior and the boundary, and also trying to understand these puzzles with black holes, these problems with black holes, quantum aspects of black holes.
But I mean, do you? Is this like your life, researching this, or is it just a job?
Oh well, it is a kind of, it's a passion, and I would like to really find the problem and find the solution to the problem, and well, I hope it gets solved soon.
Are you close?
Yeah, we seem to be close, but hopefully yes.
What I try to imagine is because it's also theoretical. You must have a big imagination. Mm-hmm. When you think about it, what do you see? Is it not? And I'm not. I don't want you to explain the theory, but how do you represent this in your head, in your brain? In colors or in shapes or in
yeah, probably in terms of but we imagine formulas and their properties, and we make a little mental image for these formulas. For example, already for Einstein's theory of relativity, you have to imagine space-time as some kind of membrane and so on.
But how do you imagine that?
Well, I imagine it for some classical space-time, for example, as a membrane, and a quantum one, a membrane that is fluctuating. And those are the kind of mental images that we...
I'm sorry, again, a membrane?
Well, space-time is like a membrane, right? That has certain shape and has some dynamics, so the shape can change. And if you get very close, this membrane has some oscillations and some structure, right? And that's what we have at short distances. I mean, yeah, that's a picture that is more or less standard for how to think about this. Now, one of the interesting things that we've been trying to understand, and we are not, well, many people have begun to notice, is that there is some connection between a certain property of quantum mechanics called entanglement. So entanglement is a funny property, funny kind of correlation you can have in quantum mechanical systems, which are in some sense stronger than classical correlations. And so before we discuss the fact that in certain quantum mechanical systems, you cannot predict the answer to certain experiment, right? So you might sometimes find 50% chance of one and 50% chance of the other answer. But you can have systems where you have two particles and they are separated, and you do an experiment here and you have 50% chance of the outcome, of each outcome, and you can do another experiment here and you have, again, 50% chance of any outcome. But it might turn out that the outcomes of the two experiments are correlated. So let's say the experiment is like flipping a coin, right? It comes out heads here, and then it also comes out heads here. And if it comes tails here, it also will come out tails here. So they're perfectly correlated. That's an example of a classical correlation. Entanglement is the fact that you can also measure another property at the same time. So of this coin, which is not heads or tails, but let's say the color. Well, this is a bad analogy because a property is quantum mechanical that cannot be measured at the same time as the original property, right? That's one of the features also of quantum mechanics, that sometimes you can have two properties which you cannot measure at the same time. So you can either ask this coin whether it's heads or tails, or whether it says black or white, but you cannot ask whether it's black and whether it's heads or tails. This is not perfect analogy because our classical variables are not of this kind. They are not sort of mutually incompatible. But you can do that with this quantum, let's say, properties. And again, you can have two particles so that if you now measure not only whether it's heads or tails, but also black or white, you have the same feature, the same correlation, perfect correlation with the other. And that's some kind of correlation that is not possible in classical physics, but it's possible in quantum physics. And we think that...
Even though there's a big distance.
Yeah, even though that there is a big distance. But again, with classical correlations, you can have these correlations because you prepare the two coins first, and then you took them apart, and then you looked at it. So in classical physics, there is no problem with this correlation. What is interesting is that you can have a correlation between observables that are mutually incompatible locally, right? By compatible, I mean that either you measure one or the other, but nevertheless, you have the correlation. So entanglement was a surprising property of quantum mechanics when it was first noticed. It was noticed in a paper by Einstein, Podolsky, and Rosen in the 1930s, and then this was a property, and now it's a quite central notion for quantum information theory, and people are using it in more practical ways. To build, it would be essential for building quantum mechanical computers and so on. But it also seems to be connected with the connections in space-time. So things that are closer together in space-time are more entangled with each other. So in some sense, when you have the quantum field theory vacuum, so the vacuum in the theory of particle physics, if you were to split it in two parts, the fundamental degrees of freedom, or quantum variables that describe it, are quite entangled with each other. And we think that in some circumstances, if you take two separate systems and you entangle them very strongly, so you could also generate some kind of quantum you can generate, a geometric connection between them, in some cases. So in some sense, through the entanglement is connected to the connectivity of space-time. So you can,
Well, I want to try to get back to the beginning again.
Yeah.
Because it's rather difficult.
Yeah.
And now you told me a lot about it, so
Yeah.
I try to recapture
Sure.
a little bit, if I'm right. But I would like to ask you to give definitions of the ingredients.
Okay.
But definitions for normal people.
Okay, cool.
Like what is time, what is space, and what is relativity.
Okay, good. So let's start with time, right? So time is what the clock measures. So now this sounds like a circular definition, but of course what's not obvious is that different clocks made in different ways measure the same time, right? But it turns out that if you have different kinds of clocks and you make them, they will all measure the same. They will measure the same. They'll give the same answer, and that you can synchronize clocks and they stay synchronized and so on. So it looks like there is something that is being measured by these clocks. So this something is the abstraction we call time, right? We have the time we feel psychologically, which is not a perfect clock, but certainly agrees with more precise physical clocks. But all clocks that measure time are made out of physical particles, and that's how we measure time. That's how we define it. And so it's an abstraction that is the thing that all these clocks are measuring. What is space? So, well, space is somehow the distance between the let's say the nothingness that exists between two objects. Right? Now, I mean, it's what's missing when you go into a crowded bus. Right? That's and so that's space. And now, what is relativity? So let's first discuss special relativity. So before, when I was discussing time, I said that all clocks measure the same time. And that is only true for clocks that are stationary. So if you have a clock here and a clock here, and both stay at rest relative to each other, then they will measure the same time. But if you have a clock here and another clock moving, right, they will measure a different time. And relativity, so special relativity, that tells us how different is this other time that the clock measures. So it's a simple law for how to find out what that. And so the theory of relativity is the theory that postulates that the speed of light is constant. It's absolute. So so he could also have called it absolute something. What's relative is time, but that doesn't mean that everything is relative.
And this the reasoning. What is light?
Well, you could replace light by other things like gravity waves also propagate at this speed. So more precisely, I should have said it's the maximum speed of propagation of signals. So the idea is that there is a maximum speed for the propagation of signals. And it so happens that light propagates at this speed. If you had a massive particle, it will generically propagate at the lower speed. But if you try to push a massive particle to move it faster and faster and faster, you could not make it move faster than this maximum speed, which also coincides with the speed of light.
And that's why it's absolute.
Yeah. And different observers would measure exactly the same speed.
So, can we go? Why do you want to know, why do you want to have an explanation for how life started?
Well, it's not an explanation about how life started, but how the beginning of space-time started, right? How time originated and what happened in the beginning of the Big Bang. And we are trying to understand it because that's something we don't know. So science is always about pushing the boundaries, and we don't. It's not just the fact that we don't know how it happened, but even we don't have a in theory that is self-consistent that could describe it. So we are even trying to find theories that could in principle describe a Big Bang. Then we'll have the problem of finding, well, that's the way our Big Bang actually happened. So that's why we think that this problem may be solved by thinking about it and then finding the theory and then perhaps making some new predictions that we could test experimentally.
Yeah, but all the time the same question arises again, but what happened before the Big Bang? Questions like that. So
right.
How do you deal with this almost impossible?
Well, I mean, the idea is to make a theory, and maybe the theory that you can make a theory which had a time before. Maybe you can make a theory where time actually starts in the Big Bang and does not have any meaning before it, so that the question doesn't have meaning. And we don't know what the right answer is. So That's what we're trying to find out, whether it's consistent. So people imagine, oh, maybe there was a time before and somehow we went through the Big Bang, but these are just words. There are no self-consistent equations that can, where you can have such a thing. And if you try to make a theory where, okay, the universe was contracting and then expanding again, for example, they violate some principles that we think should be true in a theory of quantum gravity.
When did you yourself ask this question for the first time?
Well, I guess as I started learning more about physics, I started recognizing where the boundaries of physics were. And there are boundaries of physics in many directions, in the direction of very complex systems, in very different directions, but this is one of the directions in which we see a boundary, and so I wanted to go to the frontier in this direction, right?
Yeah.
So I guess the physics we are trying to always push the frontier further and further away.
So right now you are at the frontier?
Yeah, this is certainly one of the frontiers.
What do you see when you look ahead?
Well, I see confusion. I see lack of understanding, and the idea is to find patterns in this confusion and to move forwards and to understand things that we currently don't understand.
Do you feel
small bit by bit? So usually you advance one step at a time, and you can get a little further and a little further. And,
do you feel something like a competitor, or something like a challenger, or something which challenges somewhat, somebody who challenges you to try to find me, something like that?
Yeah, certainly we were trying to find this answer, and we really want to get the answer. And sometimes you feel, oh, maybe it's close, but then you realize, oh, maybe they made a mistake, and then you. And it's all happening also not personally, but within a community of researchers who's trying to find this. And you criticize the ideas of others, and others criticize your ideas, and in this way you make progress, because it's a difficult problem, and you need insights from many people that know different aspects of theoretical physics or physics in general, and can inform this.
Is it possible to think of something like an entity who is on the other side of this frontier, or maybe not an entity, but
well, there might be another intelligence in our universe who has already figured out this. It has figured this out and has understood these problems, but at least it's not known to us.
But maybe, yeah. But when you are on a frontier the West was one here in the United States.
Mm-hmm.
And you don't know what's out there, but you go there and you find things.
Right.
But it's because you didn't know that there were Indians and there was another coast and another ocean.
Right.
So there is some awareness on the other side of the frontier. Only we don't know. So what kind of awareness is on the other side of your frontier?
Well, by awareness you mean the Indians. Well, that you're putting too many anthropomorphical things that are not were not present in our in this discussion. I mean, we are the only known intelligence in the universe, the only known being that is trying to understand the universe. So we are just expanding. When I say expanding the frontier, it's just understanding equations better, understanding laws of physics better. But these entities are very simple things. I mean, one of the features of physics is that I think it's amazingly interesting, is how simple the fundamental physics laws are. Of course, you might say, well, if it takes a couple of years to understand it, and you need to study, or maybe more, maybe you need to study physics for 5 years to understand them, why are you saying they are simple? But they are simple in the sense that the actual laws that govern their motion and so on are really simple. So you don't have to come up with rules and lots of books and so on. It's been very different than the laws that you find in, that the senators and people produce, where there are exceptions here and there, and there is, here there is a very simple statement, and this is followed by everything we know. So,
and it's true.
It's true to the extent we certainly have been able to experimentally verify, and the statements are simple. They're in a language which is unfamiliar. They're in a language which takes a long time to learn, and that's what takes a long time. It's just to learn this language in which to formulate the laws. But once the laws are formulated, they're in a very simple way. Once you learn
Which one do you like the most?
Well, I think the general relativity is probably the most beautiful theory, because it translates physics into geometry, and this is a very nice theory. We don't know how to make such a beautiful theory out of quantum mechanics, let's say, but maybe it will exist at some point.
So, and what for you as a child, for example, what led to this position you have right now on this frontier? Where did it start?
Well, as a child, I was watching my father, for example, fixing the washing machine and trying to learn how to do it myself. And by, again, understanding how everyday objects work, like the washing machine, the car, little radio, and so on, you learn a little bit about technology and how technology exploits the laws of physics. And that got me interested in understanding the laws of physics, which underlie technology, and seeing how far they are understood and what things are known, what things are not known. And
how did you do that as a child?
Well, as a child, I was mostly interested in technology and how things worked. Then when I was in high school, I was a little more interested in the laws of physics and chemistry.
But what did you do to explore as a child?
Well, mainly taking things apart and seeing how they worked. That's basically the process.
Yeah?
Yeah.
And putting them together again?
Yeah, it's taking them apart, putting them together. It's just learning to fix household appliances.
Yeah, that's practical, but
yeah.
I mean, if you try to find out how it's made and why it works, of course, I guess.
Right. Yeah, I was always curious in understanding how things work. I mean, how does the TV work? How does the radio work? What's the actual principle it uses, right?
And do you know now?
Yeah, I think I know the basics. Wouldn't know all the details, I guess, of technology, which are, again...
But you know, you can you know how a television works because you understand the physics inside. Or is it like comparing it to the laws of physics?
Well, the TV or any simple or any machine, even simpler perhaps, it's better to think about the simpler machine first. It has different parts and they work together towards each part is there for a reason, and they work together to make the machine work, right? Well, most of our everyday machines are, the television is made out of electronic circuits that move currents around, and they show the light on the screen and so on, and that makes the television work, and you have to understand how that is made.
Yeah, but as a child, what was your age that you did that?
Well, maybe when I was perhaps from 8 to 12, we would be doing this thing of taking machines apart and putting them together.
What did your parents say about that? Don't do it again?
Oh no, my dad liked to do this himself, so...
Oh,
yeah.
So taking things apart, you learned from your father.
Yeah, that's right. Mm-hmm.
And what did your mother say about it?
No, my mother liked it to have things fixed. So yeah, my dad always liked to fix things. He was very practical, and he liked the challenge of fixing it. And then sometimes you don't know how it works, so it's nice to have to fix something you don't know exactly how it works, and then you manage to understand how it works.
So when you're on the road and your car has a problem, you can fix it.
Well, I was able to do that in the past. Now cars got more complicated. I don't know. This car hasn't broken down recently, so I can't tell for sure. But
But it started all at a young age, and
Yeah.
and it's almost you inherited from your father,
right.
and now you are here at Princeton Advanced Studies
Yeah, yeah.
Institute. Uh, in a position where you are allowed to think as much as you can.
Right. I'm encouraged to think and do research all the time.
So, is it too simple to say that your job is thinking?
Yeah, it's thinking, it's discussing, it's learning what other people are thinking, and reading what other people write, and trying to make progress. Right. And,
Are you thinking all the time?
Well, I mean, no. I mean, I'm reading what other people write. I'm listening to other people's ideas and presentations. I'm discussing with my colleagues. We're, writing formulas and.
But can you decide? Well, now I start thinking, or does it happen, or how does it work? This thinking process.
Well, I guess the thinking normally you try to. These problems sound very vague and grand, but we try to think on very concrete problems where we can make progress, right? So there are the questions that are extremely interesting, but almost impossible to solve. There are questions which are perhaps too easy to solve, and we try to be in between. So try to find the most difficult or most interesting question that you can actually say something useful about. And lots of thinking is trying to focus on such questions, as try to imagine very simple toy models or simple models where we could say something new.
So, but maybe a few easy answers together might solve a more difficult answer.
Yeah. So it's this thing that I was saying before, that you do a step at a time. So we have to figure out where we do the next step. So the next step is in something we more or less know, but moves us in the right direction, from which we can get a better view for what the next step would be.
So when do you do your best thinking?
Well, I think during the day, and maybe.
It's not that you are when you are out, for example, when you are outside, or when you under the shower.
No. It's mostly I would say in my office, talking to other people. Normally, when you talk to other people, you get new ideas, and usually many times new ideas come together in this.
But then those colleagues are gone, and then you have to write down the idea, or do you have to
many times
materialize
we write them together, and we certainly write articles with other people, and this is important. I mean, most of my articles are with other people, so.
Oh, of course.
With other collaborators.
Yes.
So.
Yes. So it's once someone said, it's hard to sit. It's harder to it's hard to sit and not to think.
Mm-hmm.
It's so hard to shut down your thinking.
Mm-hmm.
Is it? How do you think about that?
Well, certainly I guess you have to be a little bit obsessive sometimes to work on these problems, because you want to think about this problem and you have to ignore other things. I mean, it's easy to get distracted and think about something else when you're not making progress. So if you're trying to solve a problem and you're not making progress, it's easy to get distracted. But sometimes you need to keep trying to find solutions to that problem you initially set out to do, and be slightly obsessive about it, and then you can make some progress.
And you are obsessive?
Slightly, yeah.
So when there's something distractive, what is your distraction?
Well, I mean, it could be some other interesting idea in some other slightly different field, or I mean, sometimes it's good to be distracted. Maybe the problem you're trying to solve was bad, and so it's balance. Yeah.
So well, you can say that this is what you're good at, and you made progress and new solutions or answers. Mm-hmm. Is there also an area in which you are unable to find the answers? the opposite of your talent?
Yeah, I'm not sure. Fashion.
Yeah. You cannot describe that into one equation. Or,
Yeah, that's right.
but I mean, in your character, you are obsessive for finding answers in this theoretical field. But it's also when you find it, you can write it down in one line, and then it's true. Right. Unlike political laws, with all the kinds of. So what is the area?
Well, I mean, when you write down, I think the process is not that you write down a formula and it is true, right? So normally in physics, the process is that for some physical theory to be true, it has to be compared to experiment.
I'm sorry. Yes, I understand what you mean.
Yeah, and it's checked against the experiment, and then we become more sure that it's probably true.
Yeah.
There can always be some other experiment that contradicts it, but as many experiments agree with it, you feel more and more confident.
Yeah, I'm sorry to say that. Then I say then it's true, but
at least I mean, well,
they agree on it.
Yeah, many times I mean, a lot of our work sometimes is to derive some mathematical relations, like. And the reason for this, that some of our works is mathematics, is because the laws of physics are written in this mathematical language, and sometimes even laws which are in principle simple, like these equations of Einstein, which are simple to write down, but they're very difficult to solve. So you need either computers and with some ingenious ideas to solve the equations, but once you find, for example, a solution of the equations, you can check that it is a solution. So, and then it becomes a true solution. So that's an example where...
Yeah, I understand.
But that's, you could say, well, it's mathematics, right? It's within the... So if you assume the equations are the correct description of physics, this is a solution of the equations.
And correct me if I'm wrong, but mathematics is like an instrument for you to understand what you need to understand, what you want to understand.
Exactly, yeah. So before we were talking about the language in which these laws are written. And this is a language that is fairly mathematical.
Yes.
And so you need to know enough mathematics to be able to understand the...
Yes. So, but I can imagine that this mathematics, you are talented for using it. It's a way to look around you and follow your obsession. But there are also very much a lot of areas in which mathematics just doesn't work.
Mm-hmm.
So then you which areas are that you cannot use math?
Well, there are many areas of our everyday life where we don't necessarily we don't use math. I don't know, if I want to learn the piano, math is not very useful. Or if I want to play soccer, I don't know, learn to play soccer better. Math is not very useful. I just have to practice playing soccer, right? Or if I want to cook better, my lunch or cook a nice meal, math is also not very useful. So there are lots of areas, but
so what are the things you are not good at?
I don't know, playing soccer and sports.
But do you like it?
I do it sometimes. Yeah.
Is that an aspect of mathematics as well, that you can like it?
If I like mathematics because of some aspect, well, I like some aspects of mathematics because it's first it's a nice tool to describe physics, and I certainly like it. It's interesting, and well, mathematics is also a subject on its own that is huge. I know a little bit of mathematics, and I try to learn the mathematics that I think would be useful for this problem. And sometimes people need to invent some new mathematics to solve this problem.
Yeah. Well, but for example, I'm much more comfortable when I talk to people, trying to understand people. Mm-hmm. But I'm not comfortable when I talk with other people about mathematics, because it's not my thing or my talent or so I choose the things in which I'm comfortable, and that's what I'm doing right now. I'm filming, interviewing people, trying to how does that person work?
Right. Well, that's true. I mean, we all know what our strengths are, and we try to do an activity where we can really use our talents, right? And yeah, suddenly I would be a very bad interviewer. Know what the other person is thinking or try to guess it. But yeah, we all do these various talents, use our natural, or we develop certain talents, and I guess through the path of our lives, we continue developing them, and we get better at those sub areas, right?
Yeah. Anna told me about because I don't want to forget that one. Two stories you told about the mountain and the valley.
Yeah.
And about Romeo and Juliet.
Oh, okay.
Okay. So, is it? Do you think it's interesting to tell that? It's for understanding your theory.
Yeah, I'm trying to remember what the story about the mountain and the valley was.
That if you live in a mountain or in a valley, and you have no reason to go up on the mountain because you cannot grow corn.
Oh, yeah. This was. I think the original question was whether this is useful for anything, or what are the technological applications of this research or this area of research. And this area of research doesn't have a direct technological application that we know of. So we do it because we want to know and we want to understand. And an analogy is that to think that we have, let's say, a town that lives in a valley, and the valley is fertile, and they grow corn and they grow their food in the valley, and there's a nearby mountain, and there are some mountains surrounding the valley, and someone might decide to go up the mountain just to see what's there. Now, the expedition of going up the mountain might be totally useless for growing better corn, or you will not plant anything nice in the mountains. But suddenly going up the mountain might give you a better view of the valley, might help you understand where this valley is located. And it might allow you to see another valley, but this is not guaranteed. Maybe there are all mountains and there's no other valley. But it's suddenly part of the curiosity of seeing where we are and to extend the frontier to really understand better where we are sitting in the universe.
Yeah.
And this is one direction in which we can go, and certainly that's what it's like a mountain that is there, and we're trying to go to the summit and be able to understand. The summit is understanding the Big Bang singularity, so understanding the beginning of the Big Bang. And we'll try to climb this mountain, and
where are you on the mountain?
Well, we don't know, because we don't have a view of the mountain from outside, so we only know that we are climbing. So I think we are confident we are climbing. We are not going down, so there must be a summit.
Yeah, that's a nice one.